And that kind of leads us perfectly into the next essay, which is all about this really mind-bending concept called chaos theory.
Chaos theory. Okay.
Yeah,
That sounds a little intimidating, but I have a feeling you're going to make it surprisingly relatable.
I think so.
All right, ready to dive in?
Yeah, let's do it.
Yeah.
Yeah, so, sometimes the most complex ideas have these really surprisingly simple origins.
Okay.
Like chaos theory.
Okay.
It all started back in the 1960s with this meteorologist named Edward Lorenz.
Okay.
He was running these weather simulations on his computer, and just totally by chance, he discovered something incredible. These tiny, almost imperceptible changes in the starting conditions could lead to dramatically different weather patterns down the line.
Wow.
And that's what we now call sensitive dependence on initial conditions, or as it's more commonly known, the butterfly effect.
Wait, so you're saying something as small as a butterfly flapping its wings in Brazil could eventually cause like a tornado in Texas?
Well, it's not quite that literal, but, the principle holds true. In these chaotic systems, even the smallest changes can have huge and unpredictable consequences. And that got scientists thinking, what if chaos theory could explain those wild population swings we see in nature?
Okay.
I mean, we were just talking about how quail populations can just boom and bust seemingly at random.
Right.
So what if there's some kind of underlying order to that chaos?
Okay, so you're saying those seemingly random fluctuations might actually be part of a larger predictable pattern.
Exactly.
Okay, I'm trying to wrap my head around this.
Yeah. It's definitely a mind bender. So let's take it back to the 1970s with this guy, Robert May.
Okay.
He was studying population growth models. These are basically mathematical equations that try to predict how populations will change over time.
Right.
And May found that even a really simple model with just a few parameters could generate all sorts of different outcomes depending on the growth rate.
So you mean like a small tweak to the growth rate could make the model go from stable and predictable to completely chaotic?
Exactly. And that was a groundbreaking discovery because it showed that even these simple systems can exhibit this incredibly complex behavior.
Wow.
And guess what?
What?
Quail, with their high reproductive potential and their sensitivity to environmental changes, they fit the bill for potential chaotic dynamics.
Now you really got my attention.
Oh.
So does the paper actually connect this chaos theory to real-world quail populations?
It does.
Okay.
The author highlights several research studies that actually explore this very question. One study was looking at a computer model of a quail population, and they found that these populations could experience those boom and bust cycles even when the death rate stayed constant.
Wow.